Chloe Dawson Taylor, I am 5'6" 3/4" and I weigh 130 pounds. And this is physics.
Now let's take a look at kinematics and Chloe's max speed. To find Chloe's initial velocity, we're going to time how long it takes her to go from the flags to the wall and do her flip turn. Then we're going to divide her displacement of 5 meters that it takes to get from the wall to the flags by her time that we have found. If you're wondering why I decided to find Chloe's velocity initial from the flags to the wall, as opposed to from the start of her race with her dive, it is because the acceleration from the dive is so great that it would have made her velocity initial average inaccurate. Let's fast forward to find her second velocity. To find Chloe's final velocity, I timed how long it took her to travel from the flags to the wall, where the displacement is 5 meters. I then divided her displacement of 5 meters by the time it took her to travel that distance, and found her final velocity to be 1.4 meters a second. Since Chloe's final velocity was 1.4 meters a second and her initial velocity was 1.3 meters a second, it can be determined that her max speed was her final velocity of 1.4 meters a second. Since it is easier to keep an object in motion than to get it started moving, it makes sense that this would happen considering that the force of friction static is greater than the force of friction kinetic. To find Chloe's acceleration, we must first find total time. Now since our initial and final velocities are averages, we must divide the time we found for both of them by 2. Since velocity initial average and velocity final average, which we have already found, are perceived as the velocities in the middle of that time period, since they are averages. And therefore, if we divide both delta t1 and delta t2 by 2, we can find this middle time value. We can then add both middle times for velocity initial and middle time of velocity final with change in time 3. Change in time 3 represents the change in time it took for the swimmer to get from where we found her delta t1 to where we found her change in time 2. I have timed and recorded this value in Chloe's swim and found it to be 13.6 seconds. Now that we have delta t total, by adding all 3 changes in time, we subtract our final velocity, which we already found, in the max speed question by our velocity initial. We then divide this value by our newly found delta t total to find acceleration, which is 0.006 meters a second squared. After calculating our displacement and time, our unknowns are velocity vertical final and velocity horizontal. With our givens, I have calculated the velocity horizontal and velocity vertical final. Let's move on to forces with Newton's first law. Let's relate Chloe's flip turn to Newton's first law. Chloe is in motion going into the wall at a constant velocity and direction. When she is approximately 0.2 meters away from the wall, Chloe applies an unbalanced force by applying a downward force on her head and applying force to her thighs to curl them against her body. Chloe is able to change her motion and speed of direction by applying an unbalanced force to her body. Newton's second law states that force equals mass times acceleration. Using Chloe's acceleration already gathered in kinematics and converting her weight from pounds to kilograms, we can find the force she applied in her race. Newton's third law states that for every action there is an equal and opposite reaction. Here we see Chloe using her arms to propel her through the water. Her arms are pushing the water backwards and behind her. For this action, the reaction force is the water then reacting and pushing her forward, which is the opposite direction from which she originally pushed the water. Now let's apply Newton's third law to a swimmer's push-off. For the push-off, a swimmer applies a force against the wall. For this action, the reaction is an equal force, which is the reaction force, is applied back on the swimmer and pushes them off the wall. Let's now look at the types of forces involved. Because Chloe is not yet in the water, the only forces that act on her are force of gravity and force normal, and they are both equal. These are the forces that act on a swimmer. Because force of buoyancy and force applied are greater than force of gravity and force of drag, they have longer arrows. The total force of drag on a swimmer is composed of frontal resistance, skin friction, and eddy resistance. Back at the 2009 Beijing Olympics, swimmers everywhere were shattering world records. The reason being they had bought a suit that dramatically decreased their skin friction in the water and increased their buoyancy so that more of their body was out of the water, which decreased their frontal resistance. The Laser Racer bathing suit by Speedo did all these things, while also costing $1,000 each. making it unfair to the non-elite competitors at the Olympics who couldn't afford it. One of the reasons why the suit became banned in 2010. Now, how did the suits do it? The answer is that they were made of polyurethane, a fabric designed to imitate a shark's skin and therefore not absorb any water. The suits were also shoulder to ankle in length and tight to compress your surface area. Lastly, the suit trapped air inside it before the race, adding buoyancy and reducing drag. Now that we've learned about the laser Speedo bathing suit, let's draw a free body diagram of the forces that would act on a swimmer racing in one. As you can see, all 4 forces that would apply on a swimmer in a regular bathing suit apply on a swimmer in a laser racer bathing suit. The difference is the force of drag is greatly reduced and the force of buoyancy greatly is increased due to the air being trapped within the suit. Force of drag is being reduced because of the frontal resistance that the suit is compressing. Force of drag is also being reduced due to the swimsuit's imitation of a shark's skin, which means that it does not absorb water, it repels it. Force of applied and force of gravity remain the same. Using the force gathered already, we're going to find out how much work Chloe did in her race. To find change in displacement total, we add change in displacement 1 and change in displacement 2, which we already gathered in kinematics. We then add change in displacement 3, which is the distance between the first 2 displacements. We then multiply our newly found change in displacement total by force net that we've already found. Work is then 10.6 joules. Now to find power, we need to find the total amount of time it took for Chloe to swim the 30 meters, which is delta T1 plus delta T2 plus delta T3 for a delta T total of 21.3 seconds. Now that we've found total time, we then divide work, which we already found, by change in time total. Therefore, Chloe's power is 0.49 watts. Energy cannot be created or destroyed, so let's take a look at the change in energy in Chloe's dive. At the beginning of her dive, she only has energy potential, because she is at a height and the force of gravity has the potential energy to bring her to the surface of the water. As she dives off the diving block, this potential energy begins to change into kinetic energy, so that by the time she hits the water, there is no energy potential left. It has all been transformed into energy kinetic. As Chloe enters the water, a marginal amount of her energy kinetic is transferred into energy sound from her splash and energy thermal. Although these energy amounts are minimal, so most of her energy remains as energy kinetic as she begins her race. Here are the calculations for energy potential being turned into energy kinetic.